Before we proceed further, you should be clear with how to find the direction of electric field. Here I have the first case with a positive source charge, and suppose we are to find the electric field at point P. We know we have to find the electric field magnitude by writing E equals to 1 by 4 pi epsilon naught, the source charge divided by the distance square. In order to find the direction of electric field at point P, we are going to join point P and the source charge. After that, we are going to place a test charge which is going to be positive at the point P. Now you have to check in which direction this positive test charge is going to move if we simply release the positive test charge at point P. Clearly, this is positive test charge and the source charge is also positive. The test charge is going to be repelled by the source charge and the direction in which it's going to move is this. This is what is the direction of your electric field as well. So in simple terms, wherever our positive test charge is going to move, that direction is the direction of your electric field. In the second example again, if you look, we have a negative source charge. Again we have a point P where we want to find the direction of electric field. I'm going to take the test charge, place it at point P. The test charge again I'm going to take positive. We are never going to take a negative test charge, but our test charge will be always positive. When we do that in this case, this positive test charge will be attracted by the source charge and is going to move in this direction, that is towards your negative source charge. This is now what is known as the direction of your electric field. So you can see, for a positive source charge, the direction of the electric field is away from it, whereas for a negative source charge, the direction of electric field is towards it. As we look at some more cases later, you will become more clear with the direction of your electric field. In our next topic, we are going to see how do we find the electric field intensity at a point when we do not have a single point charge, but we have group of charges. In this example, you can see we have a source charge which is, let's say, Q1, we have a source charge, let's say Q2, Q3 and n number of them. The last charge is your Qn. Here the electric field is created not only by the source charge Q1 but by all the other charges present in this system. To find the electric field at point P, if E1 is the electric field at point P due to the source charge Q1, E2 is the electric field at point P due to the source charge Q2, E3 is the electric field due to the source charge Q3 and so on, then the net electric field is going to be the vector sum of all these fields added up. Of course, using proper vector addition laws. To represent that in this diagram, if I tell you that all these charges are positive right now, the electric field at point P due to the first charge will be in this direction with some magnitude. Let's write it E1. The electric field due to charge Q2 will be somewhat in this direction. The electric field due to the third charge Q3 will be in somewhere this direction, and so on. Clearly, to find the net electric field at point P, we must add all these fields because they are vectors, and we can apply rule of vector addition for them. You can say we are again using superposition principle to add all the vectors to get a net vector. Next, we are going to learn about a very important topic, that is your electric field lines or electric lines of force. In this topic, you are going to see how do we represent an electric field in a given space. And this electric field can be represented by so-called electric lines of force or electric field lines. We have a very simple rule for drawing these field lines, and these field lines are going to tell us about the electric field in that region, giving us an idea about the magnitude as well as direction of the electric field at every point in that region. Let's read once the definition first. An electric field line is a path along which a small positive test charge would move if it is free to do so. What it means is that, suppose we have a source charge of plus Q, and of course we know that this source charge will create electric field around it. That means it is going to apply force on other charges. According to definition of your electric field line, we are going to take a small positive test charge, let's say plus Q naught, keep it at any point that we want. Let's say we've kept at this point. When we suspend this positive test charge near our source charge, we are going to see that this test charge will be repelled by the positive source charge and has to move away from the positive source charge along this path. This line that I have drawn, I have to call it electric field line. Similarly, if I would have kept that test charge somewhere here, that test charge would have had a path away from the positive source charge and it would have looked like this, straight line. So again I can say these two are the field lines that I have drawn. Obviously, if I keep the test charge here, that test charge again will be repelled by your positive source charge and it's going to move away from the center of your source charge. When I keep the test charge here, again I can say it's going to move away in this direction. If I keep the positive test charge here, it's going to move away from the source charge. If I keep the positive test charge here, it's going to move away in this direction, and so on. So you can see we have drawn not only one but many such lines, and all these lines you can see they represent the path followed by your test charge, the positive test charge, when we keep that positive test charge near to our source charge. Now the question is how many of them we have to draw. Here you can see we have drawn 8 lines, 1, 2, 3, 4, 5, 6, 7 and 8. And suppose this charge that I have taken, the source charge is, let's say, 1 coulombs. If we had a source charge of, let's say, plus q of course, but this time 2 coulombs, notice we'll again get these field lines drawn as usual. This time we should not draw 8 lines, but this time we should represent it by 16 lines. Now why have we done that? Because in our representation, 1 coulomb of charge, we are drawing these lines of force, 8 of them. So when we double the charge to 2 coulombs, the number of lines in our representation should be 16 lines. The reason is simple. Our electric field is directly proportional to your source charge. So if I have a bigger source charge, I am going to get a bigger electric field. And to represent a bigger electric field, we must draw more number of lines around the source charge. Clearly you can see we have doubled the charge from this case to this case. We should have double number of these field lines. One more thing you can note is that the crowdedness of the lines in the first case compared to the second case is quite less. This crowdedness or the density of these lines is going to tell us about the magnitude of the electric field. And the direction of electric field at any point is found by looking at the direction of these lines of force at that point. That's why we have drawn this diagram here. You can see in this diagram we have a single positive source charge plus q, and we have drawn electric lines of force due to this positive test charge, source charge. And I can say all these lines are radially outward. Radially outward here means that these lines are coming out of the center of your source charge. Then suppose if you have a negative source charge, and if I take a positive test charge near it, you will see that this positive test charge will be attracted by your negative source charge. So this line here clearly shows the path followed by your test charge when I have kept the test charge or suspended the test charge freely in this field. Again, if I keep the test charge somewhere here, the positive test charge, this test charge will be pulled towards the center of your negative source charge. When I keep the test charge here, it will be pulled in this direction following this path. So this is also a line or electric line of force. If I keep the positive test charge here, it's going to move in this direction again, you can see. So similarly, we can draw all such lines here. Notice this time I have to say that these lines are radially inward. That means towards the center of your source charge. So clearly you can see the direction of the electric field, which is given by these lines, are opposite in direction when we compare to a positive source charge and negative source charge. For the positive source charge, expect the electric field to be away from it, and for a negative source charge, expect the electric field lines to be towards it. And again, suppose if I compare two cases where we have 1 coulomb of negative charge and let's say minus 2 coulombs of another negative charge, you can imagine that we have to draw this time not 8 lines, but we have to draw now 16 lines, all radially inward. So here we have that case. The electric field lines drawn for a negative source charge, they all should be radially inward in direction. Next, we are going to take up a case where we do not have a single positive charge, but we even have your negative charge. Let's say this case where we have a positive source charge, separated by certain distance from a negative source charge. Here I've written plus q and here I've written minus q. To tell you both are same in magnitude. That means if this is plus 1 coulombs, the other must be minus 1 coulombs. Let me show you how these lines are drawn now. So this is our plus q charge and let's say this is our minus q charge. Let's say this is the line joining the center of the two charges. Now to draw the electric lines of force or electric field lines, you have seen we must take our positive test charge. Let's put that positive test charge at this point right now. Now this positive test charge, when we suspend it freely in this field, you will see the positive source charge is going to repel it in this direction, sending it away from its center, whereas the negative source charge is going to attract test charge in this direction, the positive test charge. Clearly both the forces are acting towards the negative source charge. So clearly this positive test charge is going to have a path or have to follow a path in this direction. That's why we have drawn the arrow here representing the path of your test charge, and hence we will call it electric field line. Now suppose if we have our test charge somewhere here, then this positive test charge will first be repelled by our positive source charge somewhere in this direction, and our negative source charge is going to attract it somewhere in this direction. I have drawn this bigger in length and I have drawn it shorter because the repulsive force on this charge will be bigger compared to the attractive force on this positive test charge, because you can see our negative source charge is very far and our positive source charge is very close. Hence the repulsive force is going to be stronger than your attractive force. This charge, because of which, is going to follow a path somewhere in this direction, not moving here, but in between, and it's going to be closer towards your bigger force. So I can say now the path of this positive test charge, when it's kept here, will be somewhere along this direction. Let's say the test charge has reached somewhere here. Now you can see again the positive test charge will continue to apply a force, a repulsive force, to our positive test charge, and our attractive force applied by our negative source charge will start to become bigger and bigger, and it's going to be directed along this direction. So this force, the repulsive force, is becoming smaller and the attractive force is becoming slightly bigger. Because of these two forces acting on the test charge now will start moving somewhere in this direction. Earlier, if you remember, it was moving in this direction, but now you can see the path of this test charge is going to be bent. It's not going to be a straight line. So the test charge started from here, but it's going to take a curve now because it's going to move slightly towards the negative charge. When the test charge reaches somewhere around that point, or let's say this point, now the test charge will be again repelled by the source charge, the positive source charge, somewhere in this direction, but with a much less force. And you can see the attractive force by our negative test charge will start becoming more and more, will continue to become more and more. I can say the test charge now moves in between these two forces somewhere along this direction. So what I can tell you right now is that the path of our test charge, the positive test charge, will start from the source, which is a positive source charge, but it's going to continue to move away from the positive source charge. It's going to bend and bend and bend, and somewhere in the middle you will see the repulsive force by the positive source charge will be in this direction, the attractive force will be in somewhere around this direction. And this force and this force acting at this positive test charge will be equal because the distance between this and this are same, you can see at that point, and even the magnitude of this plus q, the magnitude of minus q, they are same. Hence both these source charges will apply equal force on this test charge, because of which this arrow and this arrow should be drawn of equal length, because of which the path followed by the test charge will be in this direction. Now having reached there, after some time, now you can see the test charge is much more closer to your negative source charge and it is very far from your positive source charge. So this force, the repulsive force on the test charge, will become less now, and the attractive force by the negative source charge will be bigger. because of which the test charge now slowly will curve towards your negative source charge. So what you have learned here is that if I take a positive test charge, keep it somewhere here near our positive source charge, this test charge will be acted upon by force from both the positive source charge and the negative source charge, and it will start moving away from the positive source charge, taking a curve and finally reaching to your negative source charge. So I can say again, this is the path followed by your positive test charge, and this is what we have to call as electric line of force. Similarly, you can see if I would have kept the test charge somewhere here, then again the path followed would have been somewhere in this direction. If I have kept the test charge somewhere here, it would have followed this path. If I would have kept the test charge somewhere here, it would have followed this path. One thing you need to note here is that as I'm moving away and away from both the charges, let's say from this point, and I need to draw a line somewhere here, I have to keep a gap between these lines. You can see this gap is quite large. The reason being that to have a smaller electric field compared to this region. So region B should have less electric field compared to region A, because region B is very far from the charges and region A is very close to the charges. And you have learned earlier, we must draw these electric lines of force crowded or with more density in regions where there should be more electric field. This diagram is represented well here. I have drawn here a very small gap, you can see, between the lines, but here I have drawn a very big gap. And finally, if I take a test charge somewhere here, that test charge will be repelled away from the source charge. So that's why we have a line somewhere here. And if I keep the test charge somewhere here, that test charge will be pulled straight towards your negative source charge. So this is how you need to draw your electric lines of force if we have a system of equal, which is your minus q and plus q charge, separated by a distance. Now this system is also known as dipole for us. System of two equal and opposite charges separated by certain distance. Next, you are going to see what happens if we take two charges plus q and the other charge is also positive and same magnitude as the first charge. So if this is plus 1 coulombs, this is also plus 1 coulombs. Let's understand how the lines are drawn now. So I've taken a positive charge plus q. I have another positive charge which is again plus q. We do not call this system as dipole because they are not oppositely charged. If I take the center of these two charges and keep our positive test charge right at the center, you will notice the first charge is going to repel it in this direction. Even the second charge is going to repel it, but in this direction. Both these source charges do not want to pull this test charge towards them, but they want to push this test charge away from them. As a result, the force on the test charge will be oppositely directed from both the source charges. Now since this point is located exactly in the middle, this force and this force applied by this charge and this charge will be equal in magnitude, but they are opposite in direction. Hence this test charge has no way of moving, but is going to stay at that point because the net force on this test charge will be 0. Hence we cannot draw, or we are not allowed to draw any path for this test charge. And since it's going to not move in any direction, we cannot draw any electric lines of force or the path. Such point we are going to call as nodal point for the system, where I can say the electric field is 0, because you can see no force will be applied by these two, or let's say the net force applied by the system of charges will be 0. So such points we will call it nodal point, and we should not draw any lines of force at that point. Now what you need to do is that wherever you get this nodal point, you are going to draw a line or imaginary line perpendicular to the axis of the charge system at the nodal point. So you can see here this line is drawn perpendicular to the axis of the system, and it is drawn perpendicular. And this line is not drawn here, but this line is drawn such that it passes through the nodal point. Now this line is going to help us because if I take this positive test charge and keep it somewhere here, the first charge is going to repel it in this direction with a very big force because it is very close to that point. And this charge, which is also positive, is going to repel somewhere in this direction. Because both the charges, the source charges, do not want this test charge to come to either of them. As a result, the net force on this charge will be not here, but along somewhere here. So I can say the path followed by this test charge will be somewhere around this direction. And it's going to take a curve, as you'll see, because when the test charge reaches here, the repulsive force from the first charge will be less and from the second charge will be a bit more. But overall effect is that the charge will start curving away from the nodal point, or let's say nodal axis, this line. So basically I'm trying to show you is that if I keep the test charge here, this test charge will start moving away from the first charge, and also it cannot go towards the second charge because both are positive and they want to repel the positive test charge. So instead of moving or crossing that nodal line or this line here, the test charge is simply going to be restricted to cross that nodal line. Not nodal line, we do not call it nodal line, but let's say this line here. The same thing happens on the other side, so you can expect to have a electric field line in this direction. And even if I keep the test charge somewhere here, you expect the same thing. The lines not to cross this imaginary line. So if the test charge is kept here, the test charge, again I can tell you, will be repelled from the first charge and also from the second charge, and is going to take a curve away from both of them. Like this, you can draw many electric fields as you want, the lines, going away from both the charges. That's why we have this system here, you can see. Equal charges, positive and positive, so we expect a nodal point. And since both were positive, you can see the direction of these lines are away from both of them. Next, if I have the same kind of system but for your negative charges, what you can expect is that if I keep a positive test charge somewhere here, this positive test charge will be pulled by the first charge and also will be pulled by the second charge. But it's not going to come straight because even the other charge is going to try to pull it. And as the test charge comes closer and closer and closer and closer to your this charge, is going to pull towards fully by your first charge. And if I have a test charge somewhere here, that positive test charge will be pulled by your this first negative source charge. Obviously a positive test charge kept somewhere here cannot reach here because this charge is closer to your positive test charge. So it's going to take a curve and finally reach your closer negative charge. Here you can see I've drawn the nodal point again exactly in the middle because this negative source charge and this negative source charge are equal in magnitude. So exactly in the middle, the positive test charge will be pulled by the first charge, will also pull by the second charge equally, because of which the positive test charge will not move in any direction. Hence there will be no path. That's why we have this nodal point here. Now suppose we have two positive charges. One is your C plus Q1 and the other one is your plus Q2. First we are going to find where should be the nodal point. To do that, in this case let's say Q1 is greater than Q2. Now if I take suppose a point exactly in the middle between these two charges, I can tell you that the force applied by the first charge at this point will be greater than the force applied by the second charge, because the distance is same, but since this charge is bigger in magnitude, it is going to apply more force at this point. As a result, the net force here cannot be 0. But however, if you are talking about a point closer to your smaller charge, so you can see this is a point closer to your smaller charge. Now this point corresponds to a smaller distance from the second charge, but this point corresponds to a very large distance from the first charge. Clearly, if I keep a test charge At such a point, the force due to the first charge will be less as we move from the middle, and the force due to the second charge will start increasing. So there's a chance that the force due to the first charge can become equal to the force due to the second charge. Hence, such a point will represent where the total force on the test charge will be 0. Hence, there will be again no path for the test charge. So this point is what is known as now nodal point. So the important thing is that if we have a system of two unequal positive charges or negative charges such that one of the charge is bigger than the other charge, then there will be a nodal point where the total force on the positive test charge will be 0, and that nodal point is found to be closer to your smaller charge. So once we have that nodal point, you can see again we have drawn this line here, and all these lines that are electric field lines which are curving away from the positive charge and even from the other positive charge, they should not cross this line here. And you can guess how it should look like for your two unequal negative point charges. Next, we are going to study about the properties of your electric lines of force. It's very important. Conceptually also, exam point of view also is very important. Electric field lines or lines of force are continuous lines or continuous curves, and they should not have any breaks. That is easy to understand because if you remember, electric field line is the path followed by your test charge. So suppose if I have a test charge here in an electric field, and suppose this is the path followed by your test charge. Clearly the path is always going to be continuous. You can't expect the path to have breaks like this. If there is any break as such, it simply means the charge, the positive test charge is moving and has reached certain point, then it disappears from that point and suddenly appears from this point and start moving again. Clearly that cannot happen with any path for any object. Hence the lines or electric field lines, there also should be continuous and should not have any breaks. It's like you're walking and you disappear and you appear again, so your path will have breaks. But obviously you cannot do that, so your path should always be continuous. The next point is, electric field lines do not form closed loops. They start from positive charge and always should end on a negative charge. That is again easy to understand because you have seen, if I take a positive charge, the electric field lines are drawn away from your positive charge, because the test charge will start moving away from your positive source charge, because the test charge is also positive. It cannot happen that the positive test charge will start from certain point, go away from the positive source charge, and then later come back to the same point. This is not possible because the positive test charge will be repelled by this positive source charge, and there's no chance that it's going to come back. So clearly the electric lines of force cannot form closed loops. The same thing happens even if you have a negative source charge. Imagine you have a positive test charge somewhere here. This positive test charge will come closer or towards your negative source charge. So this is your electric field line, which is the path followed by your test charge. You cannot expect the test charge to reach to this point and then go back to this point. Hence, you cannot expect again the electric field line to form closed loops. The next is very important. The next point talks about the direction of the electric field. To know the direction of the electric field, at any point, we must draw the tangent to the electric lines of force or field line at that point. I'll repeat again. The direction of the electric field that we are talking about at any point can be found out by drawing a tangent to the electric field line at that point. Suppose this is the path or this is the electric field line, and I want to know what is the direction of electric field at this point. Your job will be to simply draw a tangent at this point along the direction of your path. This arrow here shows the direction of your electric field. Like for example, if you look at this case here, suppose I want to know what is the direction of electric field at this point. You simply need to come and draw a tangent to the curve that we have there, and this green arrow here represents the direction of your electric field at this point. And obviously if I'm going to find the electric field at this point, I simply have to draw a tangent again. Tangent means a line which is going to pass from the curve or touch the curve exactly at one point. So this is the arrow now which represents the direction of your electric field at this point. That is applied to all the other cases we have seen. The next one is very, very important. It comes often in your exams, in your board exams, both CBSE and MBOS. You cannot have two lines of force intersecting at a given point. You have seen how we have drawn these lines. They start from positive, they end on positive, but we have never seen two field lines crossing each other. This is not possible. Let me explain to you the reason why this is not possible. Suppose we have two electric field lines. Let's suppose they are intersecting at a certain point called P. Now what you can do here is that, what I can say here is that, or these lines are present at point P, there should be electric field at point P. We know electric field is a vector quantity, it should have some direction and it should have some magnitude. Now if you ask me, at a given point, electric field should have only one value of the magnitude and only should have one direction. Because any vector quantity should have only one magnitude and one direction. You cannot expect an electric field to have two magnitudes or different magnitudes and different direction at a given point. Hence now, if I want to find the direction of this electric field at this point P, where we have two lines of force intersecting, the possibility here is that I can draw one tangent somewhere in this direction and I can draw another tangent somewhere in this direction. Clearly you can see I have able to draw two tangents at this point. Drawing two tangents at this point means there are two directions of electric field, and clearly we have seen electric field cannot have two directions at a given point. Hence I have to say that intersection of your two electric field lines is not possible or is not allowed. So here we have the fourth point. Two electric field lines cannot intersect each other because at the point of intersection we can draw two tangents, and it means that there must be two directions of your electric field, and that is of course not allowed or not possible. So they used to ask the reason, so you have to write this. Next important point about these lines is that I have shown you that the magnitude or the strength of the field, whether the field is weak or strong, can be represented by the density of your field lines, that means the crowdedness. I've shown you that if I have this region 1 and region 2, clearly you can see here the lines are very much closer to each other. That means this region 1 corresponds to a stronger electric field, whereas these lines which are far apart, that is in your region number 2, the electric field here must be weaker or smaller. The meaning of stronger and weaker electric field, I think you have already learned it, so I'm not going to talk about that. Next, electric field lines are always normal to the surface of a conductor. This last point we can discuss later. Right now I am not going to talk about that.